Hi, I'm hoping this won't be too long. This is section 1.4 continued. And I just took a photo right out of your book on page 75. And we've got a new theorem. It's talking about properties of continuity. And what's important in this one is b is a real number, so it's like a scalar. And we have functions f and g that are continuous at x equals c. So what they're going to try to tell us is if we do some things to these functions that are continuous, then they're still continuous. So the first thing is if we have this function f and it's continuous, then it doesn't matter if we multiply it by a scalar, it's still going to be continuous. So if you have this x squared plus 8, continuous, and if you take it and you multiply it through by a 3, it's still continuous. That's all step 1 says. Step 2 says the sum or difference. So if f is continuous and g is continuous, the function that you get when you add them together is still continuous. Or when you subtract them is still continuous. So if you've got a quadratic and you've got a linear function, individually they're both continuous. And if you were to take them and add them together, the function that we would get as a result is still continuous. So that's what sum or difference means. Product is basically the same. If you have these two functions again that are continuous on their own, if we multiply them, it's still continuous. So x squared plus 8 times x plus 4, we're going to end up with some type of polynomial, foiling. First, outer, inner, last. And all polynomials are continuous, so it's still okay. And the one that would probably worry us the most is this quotient one, because we know we're sensitive to division by 0. So if you've got this one that's continuous and you divide by another one that's continuous, then this resulting function is continuous as long as the denominator at that c value is not equal to 0. So as long as g of -4 is not equal to 0. So this one would have an issue. Okay, and this, I thought this was hugely important, and I would just take a picture of it too. It's important for you to be able to recognize functions that are continuous at every point in their domains. So if you have a polynomial function, and there's that great definition of polynomials that we looked at in pre-calculus, it's kind of confusing looking, but if you have a polynomial function, it's continuous at every point in its domain. Rational functions are continuous except where their denominator is equal to 0. And that's what this quotient was saying, except when the denominator is equal to 0. Radical functions are continuous. A radical function would be like a square root function going that way. It's got a definite beginning, but it's continuous. And trig functions are continuous because they say at every point in their domain. You might think, well, tangent's not continuous. It's got those asymptotes, and it looks like this. Well, the domain, though, of tangent is in between negative pi over 2 to positive pi over 2. Or it's all real numbers except, I think we said it, except n pi over 2, where n was an integer. So those numbers are already excluded from the domain. So it says it's continuous for every point in the domain. So for every point in between those points that have been excluded, it's continuous. So, so combining with this list, we see there's a whole lot of functions that are continuous. So how do we use that? So example 6. I will actually do example 6 with you in class tomorrow. So the last thing I wanted to talk to you about on this video is the intermediate value theorem. And it says, if f is continuous on the closed interval AB, f of A is not equal to f of B, and k is any integer between f of A and f of B. So, my goodness, what are we talking about? So we have a graph, and it's continuous on a closed interval. F of A is not equal to f of B. So just for, I'm going to put A here and B here. I'm going to make it be continuous like this. And f of A, function's value at A, is not equal to the function's value at B. So we've satisfied that. The first part, closed interval, we have closed circles here on the endpoints, so we've satisfied that. K is any number between f of A and f of B. So K is any number between, this would be f of A, this y value, and this would be f of B. So K is any number in between them, like right there. Then there is at least one number, C, in the closed interval AB, such that f of C equals K. So they're saying, if this is a continuous curve, and this y value and this y value are not equal, and K is somewhere between those y values, then there is some number C between A and B such that the y value at C, f of C, equals K. So consider like drawing a dashed line through K. That dashed line, that K value, crosses my function, and that right there, too many colors, that right there, this point, is f of C, which is equal to K. I'm going to read this remark below. The intermediate value theorem tells you at least one number C exists, but it doesn't provide a method for finding C. Such theorems are called existence theorems. So we're going to guarantee you that this number exists, but we're not going to guarantee you that you're always able to find it. So that's just a thing. So here's the example for the intermediate value theorem. It's a great example, and then we'll stop. So as an example of the application of the intermediate value theorem, consider a person's height. A girl is 5 feet tall on her 13th birthday and 5 feet 7 on her 14th birthday. So the intermediate value theorem says, well, I'm going to choose a height. I'm going to say 5 feet 4 inches. The intermediate value theorem guarantees that there was some point in her life between her 13th and her 14th birthdays that she was exactly 5 feet 4 inches tall. You just think about how people grow. You don't just go from 5 feet to, whoops, I woke up the next morning, I'm at 5'7", just instantly. Or we don't have people just shooting up an inch as they're walking down the hall. It's a continuous, gradual thing. So it makes sense that sometime between those birthdays, that as she was going from 5 feet even to 5 foot 7 inches, that she would have passed through the height 5 feet 4 inches. And that's the intermediate value theorem in a real world example.